Hello everyone, I'm Yuan. I'm presenting 3LegRace. It is a privacy preserving DNN training method that can leverage both TEs and GPUs to achieve privacy protection and also the computing performance. Yeah, so just a little background about myself. I'm a fourth year PhD student from University of Southern California. And my research topics covers various aspects about the privacy protecting in privacy protection in machine learning training. Yeah, so before I discussing the details about the paper, let me spend a few minutes on the motivation about the work. So yeah, so if you see the machine learning from data privacy protective perspective, we can categorize the machine learning into two classes. The first one is using the GPUs and TPUs to achieve a strong computing performance, but this platform lacks sufficient privacy protection on the data. So attackers can easily get the sensitive information about the data set. And another class is the trusted execution environment called TEs. By provide a very strong secure environment, the TEs can give a very strong privacy guarantee. It's very difficult for the attackers to access the sensitive information in during transmission of the data or the runtime in the TE environment. But the cost comes with the privacy guarantees the very low computing performance compared to the the GPU or TPU platform. Yeah, so the problem setting in this paper is that can we combine GPUs and TEs to achieve both performance and privacy guarantees? Yeah, so let me provide a little more context here in terms of the model inference, in terms of the privacy preserving model inference and training. So for the private model inference, we have very common, we have very famous algorithm called a slalom. So the basic idea in slalom is that in TEs it add noise to the region data and send the noisy data to the GPUs. The GPUs computing the convolution operations and have this noisy output, and send this noisy output to the TEs, and the TEs can get the region output by decrypting the noise output. Yeah, so it's very private in terms of model inference, but the issue here is that Slalom does not support model training, which is a more computation intensive task. Yeah, so for model training, there's other method like private ML or darknet. So all of this method have all of this method they're adopting multi-party computing mechanism that use jointly collaborating nodes to support its privacy protecting. So so I assume that they have non-coding GPU nodes that can protect the data, but the assumption of the non-coding nodes might fail in some cases. So if this assumption fails, any single node can reconstruct the data. So the privacy protecting is actually significantly compromised. Yeah, so here we are proposing a method to leverage the TEs and GPUs to achieve both privacy protecting and also the computing performance. The basic idea in the method SML is our method is like we first have a asymmetric decomposition framework to decompose the data into lowering part and the residuals. The lowering part has most information about the dataset, but the computation involving the lowering part is very light. On the other hand, the residuals is not a lowering, but it has less information about the dataset. So yeah, so most information, computations is actually offloaded to the residuals. So then we accordingly decompose the model into two parts. The first part is performed in TEs and read the lowering part XT. And the second part is performed in the GPUs and read the residuals XU. And if we take a closer view about the SML, the asymmetric data decomposition happens in the convolution layers. So we first decompose the data into XT and XU, and then we have the convolution T in the T is to read the XT do the secure convolutions in T's, and for XU we have convolution in GPUs to read the XU and do the convolution operations. So after we get the output of YT and YU, we combine the output in T's and apply the nonlinear operations. And before proceeding to the next convolution layers, we will do the asymmetric decomposition again to get the lowering part and the residuals. Yeah, so here we summarize the contributions in this paper. The first contribution is that we develop this asymmetric data and model decomposition by using a lightweight SVD algorithm. So the computation complexity in T is computation complexity in T is increases linearly with the number of principal channels in T. And given the lowering data in the input, lowering structure in inputs and the intermediate activations, the number of principal channels in T's can be much smaller than the number of total input channels. And if we take a more concrete example, where the number of principal channels in T over the number of total channels is 1/16, we can see that the computation complexity is in T's is much less than the complexity in GPUs. And the second contribution we have is that we have a theoretical guarantee for the privacy. So by adding noise to the residuals and sending the noisy residuals in the GPUs, we achieve the differential private protecting on the data. And compared to the method that directly adds noise to the region data, the noise required in SML is much less than the method that add noise to the residual data, add noise to a region data. So the third contribution we have is that we have a theoretical analysis on the lowering structure in models. So yeah, so to analyze the lowering structure, we first define the SVD, a metric called SVD channel entropy. And then using this metric SVD channel entropy, we measure the entropy bound in the output after every operation in scenes. Yeah, so for commonly used operation like convolution, value pooling, and batch normalizing layer, we demonstrated that output after all of these layers is bounded by the input. So that is the long structure is is well preserved in the in models. Yeah, so another contribution we have is that we have this asymmetric implementation. So this Avestimehr implementation, this framework can automatically convert a model into Avestimehr format and then initiate two parallel running context, which is GPU and SGX context. And the framework supports both forward and backward process for most commonly used models. Yeah, so we also conduct comprehensive, numerical evaluations on the Avestimehr performance. So the first one we have is the running time on most commonly used models. So if we compare the training time, we can see that Avestimehr achieve like almost 8 times faster than SGX only training in VHG network and almost 6 times faster than SGX only training on ResNet models. And also we also compare the inference time on DNNs and compare with a very famous baseline called Salman, and the inference time is almost the same as Salman, thanks to the long structures in intermediate data. Yeah, so the second experiment we run is to measure the training accuracy. So if we compare the SML and the original baseline, you can see the training accuracy is almost of using SML is almost the same as the original model. And if we compare SML with DPX, which is the method that directly adds noise to the region data to achieve the same privacy guarantee, DPX suffers a lot of accuracy drops. Yeah, so we also conduct the model inversion tests against SML. This model inversion text is a very powerful method that use any prior knowledge we have to do the model inversion. And to measure the performance of this model inversion text, we have the following metrics. The first two is piercing and SSIM. So they are aimed to measure the similarities between the training images and also the reconstructed images. And the last one is accuracy in the target model. So in this metric, we input the reconstructed images to the target model and measure the accuracy. And from this table, you can see that the PSNI and SSIM is very low. So that means there are few similarities between the training images and the reconstructed images. And as shown in the last column, if we input the reconstructed images to the target model, the accuracy is also very low. So that means the target model can not recognize the reconstructed images. Yeah, so this is like some samples, and we can see the difference between the reconstruct data and the regional training data. This, from this, samples, we can see that there's, not a lot of similarities between these two data. Yeah, so this is the experiment we want to evaluate the SML performance, and of course, SML has some limitations. And one significant limitation in the CPU-GPU communications. So to measure this limitation, we break down the running time into 3 parts: forward, backward, and the CPU-GPU communication time. So from this figure, we can see the CPU-GPU communication is very significant, especially around in the early convolution layers. It dominated the whole training time. Yeah, so one possible solution is that we can compress the data before sending the residuals to the GPUs. Yeah, so currently we are working along this direction. Hopefully we can resolve this issue. Yeah, so this is a very high-level description about SML, and yeah, so I'm very happy to take any questions if you have, and also if you read the papers and have any concerns or questions, please contact me offline, and I'm very happy to discuss with you about any potential issues in SML. Yeah, thank you.